Stop right there. Look at this massive piece of machinery. Do you honestly think a 10,000-liter industrial chemical mixing tank is just a giant, glorified metal bucket? If so, you are completely wrong. Think again. What you are looking at is not just bent steel, it is a high-precision, pressure-tested, fluid dynamics optimized engineering marvel. It is a highly sophisticated piece of heavy industrial equipment engineered to withstand extreme chemical corrosion, intense thermal cycles, and volatile internal pressures that would easily rip ordinary structures apart. Welcome back to our engineering showcase. In the manufacturing world, creating a vessel that can uniformly blend thousands of gallons of highly viscous polymers, corrosive acids, or ultrapure pharmaceutical compounds requires absolute perfection. There is zero room for error. A single microfissure in a weld seam, or a structural misalignment of just half a millimeter in the drive shaft, can cause a catastrophic mechanical failure, resulting in thousands of dollars of ruined product, or worse, a devastating plant shutdown. So, how exactly do we transform raw, flat sheets of heavy-gauge stainless steel into a high-performance, automated processing system? How do engineers ensure that the internal fluid dynamics achieve a perfect, uniform blend without creating stagnant dead zones? And what does it take to seal a rotating shaft so perfectly that not a single molecule of hazardous gas can escape under high pressure? In this exclusive, step-by-step breakdown, we are pulling back the curtain on the heavy fabrication floor. We will take you through the entire advanced manufacturing lifecycle, from the initial CNC precision plasma cutting, robotic TIG and MIG welding, and high-pressure dished head forming, all the way to the critical calibration of the heavy-duty agitation system and strict hydrostatic validation testing. This is the ultimate guide to industrial mixing tank fabrication. Get ready to see raw engineering power in action. Let's dive straight into the factory floor and see how it is built from scratch. It all starts with material selection and rigorous quality control. We do not just grab any sheet of metal from the warehouse. The integrity of the entire industrial process depends on choosing the exact metallurgical grade. For standard applications, stainless steel 304 provides excellent durability, but when dealing with highly corrosive chemicals, marine environments, or strict sanitary demands, we upgrade to marine-grade stainless steel 316L. This specific alloy contains molybdenum, which drastically enhances resistance to pitting and crevice corrosion in chloride environments. Once the raw metal plates arrive at the fabrication facility, the quality assurance and quality control team immediately steps in. Every single sheet must undergo a thorough incoming material inspection. We do not just trust the paperwork, we verify it. We cross-reference each plate with its original material test report and mill test certificate to guarantee chemical composition and mechanical properties. Next, engineers use digital ultrasonic thickness gauges to measure multiple points across the plate, ensuring the gauge meets the precise design tolerances specified in the engineering blueprints. Even a microscopic variation in thickness could compromise the tank's pressure rating. Simultaneously, a visual inspection is conducted under high-intensity lighting to detect any surface defects, laminations, deep scratches, or pitting that occurred during transit or milling. Any material that shows even the slightest imperfection is instantly rejected. Once a plate passes this gauntlet of checks, it is stamped with a unique heat number for full traceability throughout the manufacturing lifecycle. This meticulous vetting process ensures that the foundation of our mixing tank can endure thousands of hours of intense operational stress, high thermal cycles, and aggressive chemical reactions without structural degradation. Now that the raw materials are fully validated, certified, and cleared for production, it is time to move them onto the fabrication floor where the raw steel begins its transformation. With the materials fully certified, we move directly into the cutting and shaping phase, where raw power meets micrometer precision. The flat stainless steel sheets are loaded onto a heavy-duty CNC fiber laser or plasma cutting bed. Powered by advanced CAD and CAM software, the high-energy beam slices through the dense metal plates with absolute accuracy, creating flawlessly clean edges for the body panels, nozzles, and structural supports. Precision at this stage is absolutely critical, as even a fraction of a millimeter of deviation could cause misalignment during the subsequent welding phases. Once the flat panels are cut to the exact developed length, they are transferred to the heavy-duty plate rolling machines. This process demands a deep understanding of metallurgy, as the operator must carefully calculate the material's yield strength and springback effect. The steel sheet is fed between massive, hydraulically driven hardened steel rollers. Step by step, thousands of pounds of concentrated pressure are exerted, progressively forcing the flat plate to bend into a uniform, perfect cylindrical shell. The operator constantly monitors the radius using precision templates to eliminate any flat spots, particularly at the leading and trailing edges of the plate. Achieving a perfectly round cylinder is paramount. Any ovality or deviation from a true circle would create uneven stress concentration points, potentially leading to a catastrophic structural failure once the mixing tank is fully pressurized or subjected to the intense mechanical forces of the agitation system. After the rolling process achieves the exact internal diameter required by the blueprints, the open longitudinal seam is temporarily tacked into place using heavy-duty fixtures and alignment clamps. The raw metal has now officially taken the shape of a massive tank shell, structurally rigid and perfectly prepped for the next critical phase of heavy fabrication. Now, we shift our focus to the top and bottom of the vessel, where the tank heads are engineered to handle the brunt of internal pressures and heavy mechanical loads. Fabrication of the tank heads begins with cutting circular steel blanks, which are then transferred to massive hydraulic pressing and flanging machines. Depending on the tank's operational design, these heads are shaped into specialized geometries, most commonly dished, elliptical, or conical ends. The hydraulic press applies hundreds of tons of force, progressively dishing the center of the plate into a perfect, smooth curvature. Next, the flanging machine spins the dish at high speeds while specialized rollers form the straight flange edge. This precise geometry is critical, as the curved shape evenly distributes internal pressure, eliminating sharp corners where stress concentration could cause a rupture. Once the heads achieve their perfect geometric profile, they undergo precision CNC layout and punching. Using high-definition plasma or mechanical hole saws, openings are cut for the tank's essential interfaces. This includes the main product inlets, vent lines, sight glasses for process observation, instrument ports for temperature and pressure sensors, and a heavy-duty manway for maintenance access. Every single opening is accurately deburred and beveled to prepare for nozzle fit-up. The nozzles, which are short sections of heavy wall pipe fitted with standard flanges, are then meticulously aligned and tacked onto the dished head. The alignment must be perfectly perpendicular to ensure flawless plumbing connection during final plant installation. With the top and bottom heads formed, punched, and fitted with their respective nozzles, the primary components of the vessel are now fully prepared to be joined together into a single, cohesive, pressure-tight structure. With all the primary components formed and aligned, we enter the most critical phase of structural integrity, precision welding and assembly. The longitudinal and circumferential seams of the tank body are joined using automated TIG or MIG welding systems. Automation is vital here. It ensures a perfectly uniform weld bead, precise heat input control, and deep penetration, which eliminates human error and minimizes the risk of thermal distortion in the stainless steel. Expert welders handle the intricate nozzle attachments and filleted joints, maintaining strict control over the shielding gas to prevent atmospheric contamination and oxidation. Once the physical assembly is complete, the tank must pass a zero-tolerance inspection. Gauntlet. Every single centimeter of the critical structural weld seams undergoes rigorous non-destructive testing. Technicians utilize ultrasonic testing, passing high-frequency sound waves through the metal to detect any internal volumetric flaws like microporosity, slag inclusions, or lack of fusion. For high-pressure or high-purity vessels, a 100% X-ray radiographic examination is conducted. Industrial radiation film is placed inside the tank while an external source shoots X-rays through the weld seams. Any subsurface imperfection, no matter how microscopic, will appear on the film like a fracture on a bone X-ray. If even a single defect is found, the weld is instantly gouged out, re-welded, and retested. This exhaustive quality assurance protocol guarantees that the tank shell achieves a joint efficiency of 100%, creating a completely unified, flawless structure capable of safely holding tons of volatile material under immense operational pressure without the slightest risk of a catastrophic leak. Now, we engineer the core mechanical component of the vessel, the agitation and mixing system. This is the heart of the machine, responsible for converting electrical energy into precise fluid dynamics. Fabrication begins with designing and assembling the specific impeller type required for the target application, whether it is an anchor impeller for high-viscosity polymers, a hydrofoil propeller for gentle blending, or a high-shear turbine for intense dispersion. The impellers are precision welded to a heavy-wall solid drive shaft. This shaft must undergo rigorous dynamic balancing on a specialized balancing machine. Even a microscopic weight imbalance would create severe centrifugal forces at high RPMs, leading to destructive vibrations. Next, the top structure of the tank head is heavily reinforced with structural steel gussets to support the massive weight of the drive assembly. We then mount the heavy-duty industrial electric motor and its paired helical gearbox, which provides the high torque necessary to move viscous fluids. To separate the internal process environment from the outside world, a high-performance mechanical seal or magnetic drive coupling is installed where the shaft enters the tank. This seal is precision engineered to prevent hazardous gases or pressurized liquids from escaping, while simultaneously blocking external contaminants from entering the product. Technicians use dial indicators to align the motor shaft, gearbox, and mixing shaft with sub-millimeter precision. Perfect vertical alignment is paramount. Any runout or angular misalignment would rapidly destroy the mechanical seals, strip the gearbox bearings, and cause catastrophic mechanical failure during continuous industrial production. Once fully assembled, the drive system is wired for temporary testing, ensuring the entire agitation mechanism rotates flawlessly, smoothly, and without a single hint of vibration. With the mechanical structure and agitation system fully integrated, the tank moves to the surface finishing and treatment phase. This step is not just about aesthetics, it is a critical process that dictates the vessel's corrosion resistance and compliance with strict industrial hygiene standards. We begin with the interior surface, where the raw weld seams are aggressively ground down and progressively polished using finer and finer grits of abrasive media. For pharmaceutical, food, and beverage applications, the internal surface must meet a mirror finish specification, achieving an ultra-smooth profile with a regulated surface roughness average, or RA value, of less than 0.4 micrometers. This extreme smoothness is paramount to prevent bacteria, chemical residues, or product batches from clinging to microscopic crevices, ensuring the tank is fully compatible with automated clean-in-place systems. Once the mechanical polishing is complete, the entire tank undergoes a critical chemical treatment known as pickling and passivation. Technicians apply a specialized acid solution, typically a precise blend of hydrofluoric and nitric acids, to remove any high-temperature oxide scale, iron contamination, or slag left behind by the welding process. This chemical wash strips away the depleted surface layer, exposing fresh chromium within the stainless steel alloy. The tank is then thoroughly rinsed with deionized water, allowing the chromium to react naturally with atmospheric oxygen. This chemical reaction forms a microscopic, passive chromium oxide layer across the entire surface of the metal. This invisible barrier is the tank's ultimate defense system, rendering the stainless steel completely inert and capable of resisting aggressive chemical attacks, pitting, and oxidation for decades to come. Finally, the exterior of the tank is treated with either a uniform sandblasting, a satin bead blast finish, or a high-durability industrial coating, providing a clean, professional finish that is ready to withstand the harsh, demanding environment of a modern production plant. Before the vessel can be cleared for shipment, it must survive the final and most demanding phase, testing and rigorous quality assurance. This is where the theoretical engineering parameters are put to the ultimate test under real-world stress conditions. We begin with the hydrostatic pressure test. All nozzles, inlets, and manways are completely sealed with heavy-duty blind flanges, and the tank is filled to the absolute brim with water. Using a high-pressure hydraulic pump, technicians pressurize the vessel to 1.5 times its maximum rated working pressure. The tank is held at this extreme pressure for a prolonged period, during which inspectors use high-intensity ultraviolet lights and dye penetrants to scrutinize every single structural weld seam, flange connection, and mechanical seal. There is absolutely zero tolerance for pressure drops or microscopic weeping. Next, we initiate the factory acceptance testing, or FAT. The tank's agitation system is wired to a variable frequency drive to conduct a live operational run. We run the massive electric motor and gearbox through its entire RPM range, checking for power consumption anomalies, phase imbalances, and bearing temperature spikes using thermal imaging cameras. Vibration sensors are placed at critical points along the drive assembly to measure structural deflection. Any reading outside of tight micrometer tolerances results in an immediate teardown. We also verify the exact alignment of the shaft under dynamic load to ensure the mechanical seals are operating within their specified compression limits. Finally, a comprehensive documentation package is compiled, including all material test certificates, X-ray radiographic films, pressure test logs, and surface roughness RA charts. Only when the QA/QC director signs off on every single metric does the mixing tank receive its official ASME or CE certification stamp, validating it as a fully certified, high-performance industrial machine ready for decades of continuous, heavy-duty production.